Hello, my name is Mo Ehsani. I'm a professor emeritus of civil engineering at the University of Arizona and president and CEO of QuakeWrap Inc. Let me explain why I have taken this unusual approach of educating the public on an engineering subject. As many of you know, the recent collapse of the Champlain Tower resulted in loss of 98 lives. The repair cost for that building was estimated to be around $15 million, and the lack of funds from the condo owners resulted in the delay of those repairs and the catastrophic collapse of the building. In my career, I have developed economical solutions for strengthening of structures that we have used worldwide. As I listen to the experts on the news, many of them hypothesize about the potential causes of that collapse. But no one is suggesting an effective solution to prevent future collapses. I kept wondering, what if the residents of Champlain Tower were given such options that could reduce the repair costs by half or more? Would they have started the repairs and prevented this disaster from happening? Unfortunately, we cannot do anything for that building. But there are many condo owners in Florida that are being evicted from their buildings because their buildings are deemed unsafe. Faced with high repair costs, they are helpless and desperate to return back to their homes. This presentation is aimed at those folks to educate them on other solutions that many engineers are not familiar with, because this subject is not taught in most undergraduate programs in U.S. universities. I hope that this presentation will start a conversation between those owners and their local engineers to consider these economical alternatives that are used by the U.S. military and many of our private clients worldwide. I do not like to brag about my professional accomplishments, but I think if you're going to take my advice seriously, you deserve to know my background. By the way, this video is being posted on our website at quakewrap.com/fl.php. And on that page, we will be providing a lot of supporting documents and videos of similar projects, etc., so you can judge my claims for yourself. I also suggest that you Google my name and see what you find out about all of my various inventions. I attended the University of Michigan and received my bachelor's, master's, and PhD in civil engineering. I was a professor of civil engineering at the University of Arizona for 28 years. In the 1980s, I pioneered the use of a different approach to strengthen buildings and bridges using a new type of materials called FRP. I will discuss this in more detail later. In 1994, I founded QuakeWrap, a company that specializes in strengthening of structures, and we have completed numerous award-winning projects worldwide. I am a fellow and life member of the American Society of Civil Engineers and a fellow of the American Concrete Institute. I have appeared in various media such as CNN, National Public Radio, the History Channel, Engineering News Record, etc., as an expert in the field of infrastructure. I've published extensively in various professional journals and have about 20 patents on these strengthening solutions. Lastly, I am a registered professional engineer in 18 states, including such states as Florida, Alabama, Louisiana, California, and so on. In this presentation today, I will be going over 5 different segments. A brief introduction, followed by some of the problems that are faced in such buildings in columns, punching shear failure, failure of beams and slab, and finally some cost-saving solutions. The materials that we use are known as fiber-reinforced polymer, or FRP. In one form, they are fabrics that are very flexible. As you see here, these fabrics are made of carbon or glass, and in the field, they get saturated with epoxy. Another product that we have are pre-manufactured laminates like this one. This is our PileMedic laminate that we will be using in many of these projects. And these are as you can see, they can hold their own shape. They are not quite as flexible as those fabrics. The advantages of FRP are that these materials are stronger than steel. They are extremely durable. They do not corrode. And they're very lightweight and easy to install. And all of these lead to lower construction cost. A building could fail or collapse due to a variety of reasons. But typically, in most cases, failure of beams or slab in a building are localized and affect only a small area around that element. On the other hand, column failures affect the overall stability of the building and could potentially lead to the collapse of that structure. Let's look at the behavior of columns and what problems are associated with those. I have identified 4 shortcomings in these columns. One is low concrete strength, lack of sufficient ties, loss of steel due to corrosion, and continued corrosion due to presence of moisture. Let's look at each of these one by one. When it comes to the low concrete strength, I have a case here to share with you. In 2007, we strengthened the building at 6261 Collins Avenue in Miami, not far from Champlain Tower. The owners of this 8-story building were planning to add 2 more floors on top of that building. To our surprise, when we had core samples of concrete taken from the columns and tested in a laboratory, we realized that these concrete strength were about 1,200 pounds per square inch instead of the design value, which was supposed to be 4,000 pounds per square inch. In that case, we ended up strengthening the columns in those lower floors by wrapping them in many layers of carbon fabric, as I showed you before. More recently, we were contacted by owners of a 12-story building in Miami. To my surprise, the concrete strength in the columns of this building is also only 1,100 pounds per square inch instead of 4,000 pounds per square inch. These are alarmingly low numbers. These columns have only 30% of the original design capacity. I must say that these columns look good and there is no sign of damage on them, but they're extremely weak. The only explanation that I can come up with, having run across these buildings with such low concrete strength, is just shoddy construction and lack of supervision, that most of these buildings that were built in the 60s and 70s and perhaps 80s probably are suffering from the same type of shortcoming. The typical cross-section of a concrete column is shown in this diagram. A concrete column consists of longitudinal steel bars that are shown here in solid color. And then periodically along the height of the column, these ties are placed at a spacing of S. The earlier building codes, like in the 70s and up to early 80s, they didn't require a sufficient amount of these ties along the height of the column. For example, if we look at the Champlain Tower, we see that the spacing of those ties is roughly 12 to 18 inches along the height of the column. And also we notice that for bars that have a diameter of 1.25 inches or less, they only have a very small tie with a diameter of 3/8 of an inch going around them. And if the bars are much heftier, like 1.4 inch in diameter, then they have a 1/2 inch diameter tie going around them. These small diameter ties and at such large spacing are not adequate for proper performance of these columns. Now you may ask, who cares about the ties in the column? But let's look at what happens. Here is what happens in a concrete column with insufficient ties when it is subjected to severe loading, as might be the case in an earthquake. So in recent years, agencies like California Department of Transportation have been fixing a lot of these columns in older bridges by encasing them in a steel jacket, and then the annular space between that steel jacket and the column is filled with grout or concrete. This type of repair definitely works well, and it prevents that crushing and buckling of the longitudinal bars in the columns. But I hope you can appreciate that bringing a steel jacket to the basement of a building or to the floors of a building and trying to lift that and put that in place, that's a very difficult and costly repair. The same type of repair can be done with these FRP products, as I will indicate later. The other problem is the loss of strength due to corrosion of reinforcement. We know that if the longitudinal steel corrodes and the area, cross-sectional area of those bars are reduced, that directly affects the strength of the column in axial capacity. Also, for the ties, if they start to corrode and they lose their thickness and diameter, then they also cannot provide the required or necessary confinement around those longitudinal bars, and that leads to earlier failure of those columns. So both these factors contribute to a loss of strength in the column that could result in sudden failure. The other problem that we have is the continuation of corrosion due to presence of moisture. Oxygen and moisture are the fuel to the corrosion process. This is why we paint steel to prevent its corrosion. At the presence of moisture and air, the corrosion process will continue. With every passing month, these columns in buildings in coastal areas are getting weaker and weaker. This problem is not going away on its own. Let's look at the solution that we are providing to fix these issues with these columns. I know many of these columns are in the basements where you have parking garage areas, so you don't like to enlarge the size of these columns significantly. And if that's the case, we can cut the corners of these columns as shown here, and that would limit the footprint of the repair. Then we can provide additional longitudinal steel bars for the columns. These would be drilled through the slab at those corner locations and pass from the garage level all the way to floors 2, 3, or 4, as many floors as needed. Then we will have those laminates, like those Pile-Medic laminates that I mentioned. These are laminates like this. They come in 4-foot wide bands. We would take these bands and wrap them around the column to create a shell on the outside of the column. And finally, as the next step, the annular space between this shell and the column will be filled with concrete. Now, how does this solution that we provide address those shortcomings in the columns that we looked at before? One of them was the low strength of concrete. These Pile-Medic jackets provide confinement pressure that increases the concrete strength significantly. The other problem was lack of sufficient ties, or the large spacing between the ties, if you recall. These jackets are equivalent to providing number 4 steel ties at a spacing of roughly 2.8 or 3 inches. So once the column is wrapped in this Pile-Medic jacket, the longitudinal bars in the column will never buckle. We also mentioned the loss of steel due to corrosion. Well, we are introducing some new reinforcing bar, as well as these jackets that provide strength in the hoop direction. So we are supplementing the loss of steel and making up for more than what we might have lost in the corrosion process. I also mentioned that at the presence of moisture, this corrosion will continue. Well, these Pile-Medic jackets provide an impervious shield that keeps moisture and oxygen away from the column and brings the corrosion inside of the column to near halt. Finally, as an added bonus, these Pile-Medic jackets themselves, they will never corrode, making this a durable and long-lasting repair. Another issue related to this potential failure of these buildings is punching shear. In many of these older constructions where you have a flat plate slab, overstressing of the slab could lead to what is known as a punching shear failure. Basically, in the area in the vicinity of the column, the slab would punch through the column. Now, as you can see on this diagram on the right, this was taken from Champlain Tower. In those areas that are shown in circle, there used to be a slab, and actually those cars were sitting at that slab level, and you see that that punching shear failure has resulted in that slab, and the group of cars dropped by about some 4 or 5 feet and landing on the floors or the cars below. In modern construction, to make sure that this punching shear does not occur, we use what is called a column capital or drop panel. This is basically a thickening of the slab in the vicinity of the column. Also, as shown on the right here, in some cases, additional reinforcing steel will be placed in the column or in the slab in the vicinity of that column to avoid that punching shear failure. You notice that the reinforcement in these rebars that are shown on the diagrams on the right, they are vertical legs. Keep that in mind because this is what we have to also provide to make sure that the slab gets strengthened against punching shear. Another related issue that I threw these two together here is the fact that in a lot of these older buildings, the longitudinal bars in the bottom of the slab over the column, they do not overlap with a sufficient length. In fact, if we zoom in this Champlain Tower drawings, for example, you see that. In that case, there was only a 6-inch overlap over those columns. In such buildings, if the column fails, then the slab cannot support its own weight without the presence of that column. And so you get a complete collapse or failure of the slab. And this is what often referred to as a progressive collapse. Modern building codes do not allow this, and they make sure that the engineers provide a continuous reinforcement in the bottom of the slab. Now, what is the solution that we provide for this type of punching shear look like? So we can start by drilling several holes in the slab from below. These holes are not going to penetrate through the slab, so if you are living on the floor above, you will not notice these holes punching through your carpet. Then these U-shaped stirrups are epoxy bonded into those drilled holes and anchored in place. Remember in the previous slide that I was showing you how those reinforcement for the drop panels, they had those longitudinal or they had those vertical bars. This is what we are providing as the same type of reinforcement. We can also provide some horizontal reinforcement as shown here. These can be drilled through the column and extend a few feet out on either side of the column. We provide these in both the X and Y or in 2 directions. So here is a column with the U-shaped stirrups as well as the longitudinal bars placed in all 4 sides around that column. And then at this stage, we can put a form around that and pour concrete in that and create a new drop panel right around that vicinity. So this way we can strengthen that area of the slab and prevent that punching shear failure. The other type of failure is in beams and slab. The easiest way to repair these would be with using these flexible carbon or glass fabrics that I showed you before. And in some cases, it may be required to add some steel in combination with these FRP materials. The advantage of using FRP is that, remember, these materials, they do not corrode, and furthermore, they create an impervious barrier against moisture intrusion into the beam and slab, and this way they prolong the life of the structure. The last thing that I want to touch on are some cost savings and how these things have been tested and used in the field before. I want to be clear that with my academic background, I am not proposing these solutions as an academic exercise. These materials and the techniques that I have developed, they have been tested extensively by the U.S. Army Corps of Engineers, agencies such as California Department of Transportation, National Science Foundation. These tests were conducted at University of Houston. Even in Florida, at Florida International Universities, these systems were tested for Nebraska Department of Roads. This letter that I show here is written by Dr. Michael Hammonds. He's the Senior Scientific Technical Manager for the U.S. Army Corps of Engineers. And I want you to see just one of the paragraphs at what he says. He says, during an extensive evaluation process, my technical team chose PileMedic due to their innovation, responsiveness, and ease of use. Their product was superior in terms of adaptability to pile size, logistical footprint, training requirements, and durability of the repair. Finally, he adds that further, the time required to install their product to achieve a mission-capable structure was significantly less than other products. And this is exactly what I have been trying to convey to you, that these repairs are very fast and efficient. In fact, FEMA and the U.S. Army Corps of Engineers, they have a field operations guide that this is a pocket-sized manual that they provide to engineers who visit sites after a disaster. And in that manual, there is a section about how to strengthen or shore up a column that is failing. The only product listed in that manual, as I have listed for you here, is PileMedic. And they show, even with pictures, at how you can wrap this around the columns to make sure that it is shored up and it doesn't fail. Finally, before I end my presentation, I have a few cases to share with you. One of the buildings, I kind of referred to this before, that was that Cabana Hotel that in 2007, they wanted to add 2 more floors to that building, and there were 183 columns in the lower floors that we had to strengthen. As I mentioned, the concrete strength turned out to be only 1200 psi, and so we used many layers of carbon fabric and wrapped it around the columns, as you can see here, to shore up this building and bring the strength to the desired level. The cost of this repair was approximately $750,000. If this building looks familiar to you, it's because today it is a Hilton hotel that occupies that property. Another project I have here with you is the Heritage Hotel in Christchurch, New Zealand. In February 2011, there was a magnitude 6.3 earthquake, and this 13-story concrete tower suffered significant damage. The engineers estimate to repair this building was $70 million and would have required significant enlargement of columns to the point that the building was really not going to be useful for occupation anymore. In contrast, the solution that we proposed to them using FRP technology was $19 million plus another $3 million for some accidental charges. So the total was only about $22 million. The final building that I want to share with you is the McKinley Tower in Anchorage, Alaska. This is a 14-story concrete tower. It is the tallest building that was damaged by the strongest earthquake in North America. Back on Good Friday in 1964, there was a 9.2 magnitude earthquake that hit Anchorage area, and this building was damaged. Luckily, the building, after all of the damage, it stood straight, and so they did some cosmetic fixes and moved into that building. But then, some 15 years later, the city of Anchorage withdrew the occupancy permit and demanded that the building owners fix this building. The conventional repairs that they tried, as you can see in here, they attempted those on the first 2-3 floors of the building, and then they abandoned it because of the high cost of repair. So this building sat vacant in Anchorage for 20 years until we finally provided a fix for it. As you can see in this picture, in 2004, these are some of the work that we are doing, strengthening the shear walls, as well as strengthening of the columns and the floors in this building. The FRP repair total was about $2.4 million. In fact, this repair was such a major event for the citizens of Anchorage that during our repair that summer, we were covered on their local evening news as finally this building getting fixed after 20 years of sitting as an eyesore in the middle of Anchorage. Subsequent to that repair, the building has been added to the National Register of Historic Places, and we also received in 2006 an International Concrete Repair Institute Award of Excellence for this building. We've come to the end of my presentation. I want to thank you for your attention. Again, I would remind you that we have a lot of supporting documents that we will be providing on that website, quakewrap.com/fl.php. I also invite you to visit our YouTube channel that is listed here, where we have over 120 videos of various projects of all kinds of applications of these products that you can familiarize yourself with. And finally, if you have any specific questions, please feel free to call me at the number provided below. I thank you for your attention.